So firstly, welcome to everyone to this webinar, which is the fourth webinar in the series of webinars organized by LearnCX. This webinar is titled An Insight into Meshing for CFD Simulations. Within this webinar, we will see what is meshing exactly and how it applies to CFD simulations. We will give you an introduction to meshing process, which is also referred to as grid generation process. And if you are new to the entire CFD domain, or if you have very little prior knowledge, this is a very good introduction to the meshing process, and you will get to know how to get started with CFD meshing and what all you need to learn or what all you need to be exposed to. Welcome again to this webinar, and let us begin this particular webinar now. So the roadmap for this particular session is we will have a welcome and introduction session. Then we will have the webinar presentation, entire webinar presentation, followed by questions if you have any, and then we will have closing of this particular session. So before we begin, thank you for registration and thank you for taking out your time and attending this particular session. It means a lot to us. Also, please note that this is an introductory webinar on meshing for CFD. This is a fourth webinar, and there are many more webinars that we will be organizing for free, and you can attend them for free just by logging in into our website. So this particular webinar is designed to act as an introduction to mesh generation process, which is required for CFD. So this will give you a very good prior knowledge that you will use in order to advance further in this particular field. Now, before we begin, what are we and what is LearnCX? LearnCX is an initiative of training division at CC Tech, which is Center for Computational Technology Private Limited, situated in Pune, India. We have industry-focused courses for CAD, CFD, which are available online 24/7, which you can attend by sitting at your own place, in your own region, in your own country, just by using the internet. Our model, which is a combination of interactive training through internet, helps participants to learn complex technologies with ease at any time and any place of their choice. All you need is just internet. That was about us. Now we will have an overview of this particular webinar presentation. First, we will see how simulations and meshing are connected, what is the importance of meshing within the CFD simulation process. Then we will give you a detailed view of what exactly grid or mesh generation means. After that, we will see the pre-processing process, what is called as pre-processing, and how does it work using a commercial CFD software. We will see different terminologies that are associated with meshing, such as cells, element types. Then we will show you a glimpse of Ansys ICEM CFD software, which is a commercially used meshing software in industry as well as academia. After that, we will see different types of grids or meshes. We will see what is mesh quality and what are the different parameters associated with mesh quality. And after that, we will see some guidelines which are required in order to start up or in order to begin your meshing process. What are the different guidelines in order to mesh which are applicable to any number of software, not just this particular software. And in the end, we will have meshing demonstration using Ansys ICEM CFD, which is a commercial software which is used widely. And so you will see the entire meshing process, a glimpse of it or a short demonstration of it. We have seen even in the earlier webinar that simulation is a very large field which is currently used in order to analyze or design products and processes. Within simulation, we can analyze many different aspects like structural as well as thermal and fluid flow analysis. But the basis of all simulations or basis of all simulation softwares is the mesh. So before we begin any simulation or before we get any number of results, the first thing that we have to do is create a mesh for the CFD domain or the CFD CAD model. So meshing is an extremely critical part, and without meshing we cannot proceed to solving or cannot proceed to getting any results. So meshing is an extremely important part of any CFD simulation or any CFD process. Accuracy of your CFD results are directly linked to meshing. The better the mesh is, the more accurate the results are. Almost 50% of CFD simulation time of any CFD engineer goes into meshing or mesh generation. So this is the importance of meshing, which is as important as solving a CFD model or getting the results and getting the information out of the results. So meshing is as critical part as solving the CFD model. So we will see just an introduction to the entire CFD process and where does mesh generation fit into. Mesh generation is a combination of CAD model generation as well as CAD cleanup, and together with CAD cleanup, CAD generation and meshing, it is called as pre-processing within the entire CFD process. Pre-processing means before we go into the solver, we process the CAD model or the CFD model in order to fit into the solver or provide the solver with correct information. So that entire process is called pre-processing. So within pre-processing, we create the geometry. We also clean it up so that unwanted parts of the geometry are deleted or modified. We generate the mesh as well. Then we give the boundary conditions and give the entire CAD meshed model to the CFD solver along with the boundary conditions. So pre-processing is the first step, which also consists of CAD generation, CAD cleanup and mesh generation. So you can see some of the CAD models as shown in this particular slide, and then the mesh for the CAD model is generated using a CFD software or a meshing software. The next is the solver, where we actually solve the CFD domain or solve the CFD problem. In that, we give problem specification, additional models like physics, numerical computational methods, etc. And that entire process goes into solver, and we define various parameters related to the CFD problem on the already meshed geometry. Third is extracting results out of your CFD model that has been solved, and which is called as post-processing. So in that, we understand the various results using color, contours and plots, etc., graphs, and we extract data like heat transfer coefficient, drag, lift, which is useful for designing products and processes. So this is the entire CFD process, and the mesh generation aspect of the CFD process fits into the pre-processing part. So what is mesh generation? Mesh or grid is actually defined as discrete cells or elements or discrete parts into which the domain entire CFD CAD model is divided. All the flow variables and any other variables are solved at the centers of these discrete cells. This entire process of breaking up our physical or CAD model into small discrete cells or small parts or subdomains is called as mesh generation. Why do we need mesh? We need mesh because by physics or by mathematical theory, we are solving the variables like flow and heat transfer and any other variables at these cell centers or nodes. So the theoretical methods which are used for any CFD process like finite difference, finite volume or finite element, these methods solve the variables at these discrete cells, and hence we need a mesh. There are different types of grids or cell shapes like triangles, quadrilaterals, tetrahedrals, etc., which we'll see in the coming slides. So this is a glimpse of a CFD mesh. This is just a random mesh in order to explain you the entire mesh generation process, which is created between two circles. So this is, let's say, our CFD domain, which we are going to use to solve any variables within this particular circle. So CFD domain is the space between these two circles, which is shown by these triangles. Now we have filled this space by different small triangles which are called as cells or elements. Grid or mesh is a collection of all these triangles. So this entire thing is called as a grid or a mesh. Now there are a few points to note. In a CFD mesh, the triangles collectively cover the entire space. So whatever CFD domain or whatever CFD space we need to solve, we have to fill that entire space with such type of grids or mesh. These small triangles or these small cells do not intersect with each other, and also all these triangles or all these cells or elements are connected with each other at these points, which are called as nodes. So they have to be connected but not intersecting, and they have to fill the entire CFD domain. So this is called as a grid or a mesh. Now what is pre-processing? Pre-processing collectively means CAD cleanup, CAD generation and mesh. So computational fluid dynamics, which is a method of solving governing equations or physics, which uses either of the theory like finite difference, finite element or finite volume. So for that, we need to pre-process the CAD model and then give it to the solver, where either of these methods is used in order to generate results. So pre-processing means the domain inputs which are required for solver are obtained within the pre-processing softwares, and then the entire pre-processed model is fed into the solver. Within pre-processing process, we prepare the model, the CFD model, we give it an appropriate shape and size. Then we discretize the entire CFD model by using mesh. We give boundary conditions or domain conditions in order to make sense of the physics, and then we write the output file which is given to the solver. So let's say this is a practical problem which is modeled using a CAD model which is generated within the pre-processing software or any of the third-party CAD software, and then a mesh is generated. So collectively this entire process before we actually solve CFD is called as pre-processing. It involves creating shapes and sizes and exact domain. We generally use CAD softwares like Pro-E, CATIA, etc. to prepare the CAD models for CFD. If there are complex shapes, etc., we repair these CAD models in order to prepare an approximate CFD model. We use Ansys ICEM CFD software for pre-processing. We divide the entire domain into different parts or different cells, which is called as grid. So for this particular CAD model, such type of mesh is prepared. We use different techniques like structured multiblock, Cartesian, which will be discussed in the further slides, in order to mesh this entire CAD model. Now, in practice or in actual projects, it is not possible to mesh. Most of the time, the geometries are complex, so we cannot use simple mesh techniques. So we have to use some complex meshing techniques in order to cover this model in a detailed manner or in an accurate manner. After the mesh, we put tags on the boundaries like inlets, outlets, etc. And then we feed the model into the solver software, which is if we are using any of the Ansys softwares, which will be Fluent or CFX. So this entire process is called as pre-processing. Now we will enter into the meshing terminologies. This is just a basic introduction to the fundamentals of mesh generation. So whenever we say mesh, the terminologies that come to our mind are cells and elements. So the cells or elements, like we discussed the triangles in the earlier slides, those cells and elements should be supported by the software that we are actually going to solve the CFD model, which is called a solver. So mostly there are basic cells shapes that are supported by most of the commercial softwares. Here we will discuss Ansys Fluent and Ansys CFX. So if you are going to solve a 2D, particular 2D type of CFD model, then we fill the CFD domain by either triangles or quadrilaterals. So these are called as 2D elements. If we are solving a 3D model, we fill the 3D space by either tetrahedrons, hexahedrons, pyramids, or prism or wedge shape type of elements. So these are called as 3D elements. So our entire CFD domain or entire CFD model consists of a collection of these elements or these shapes. A glimpse of the Ansys ICEM CFD software, which is actually a complete and standalone pre-processing software. You can do CAD model creation, CAD repair, as well as mesh generation within this entire standalone software. Typical task that a CFD engineer performs in these is geometry creation, import repair, mesh generation, various types of meshing techniques like multi-block, unstructured, structured, Cartesian, hybrid, etc. is available within this particular single software. You give the boundary conditions and then export the mesh to the solver. Solver can be Ansys Fluent or Ansys CFX. So what are the different types of mesh that are used in order to prepare a grid for a particular commercial or industry level problem? Now the mesh does not consist of just a single type of element or just single triangles or just single square blocks, etc. We need to use different meshing techniques in order to shape the model or in order to capture the shape of the particular CAD model. So the meshing or the mesh elements can consist of Cartesian mesh, structured mesh, unstructured, or hybrid. We will see one by one what are these. Within structured, we have monoblock type of mesh and multi-block type of mesh. This is related to the meshing technique that we use. These are not exactly elements, but this is related to the process that we used in order to prepare structured mesh. Within unstructured, we have either triangles or tetrahedrons. If the shape is complex or if the shape is particularly simple and we can capture the shape by quadrilaterals or hexahedron, we have these quadrilateral or hexahedron elements. And within hybrid, we have different types of elements. So one by one, we will see pictorially what these different type of mesh mean. Cartesian mean the entire small discrete cells that we are actually going to use in order to fill the CFD space are aligned along the orthogonal axis. So as you can see, for this particular model, since the shape is always aligned with the X, Y or Z type of axis, since the shape of each component is orthogonal, we actually can use either squares which fit these particular shapes, and those squares or those cube are actually aligned with the X, Y or Z Cartesian axis. This is the most simple form of mesh, but it does not capture the shape exactly, so it is rarely used. As you can see, the cylinder will actually not be having a smooth circular curve or smooth cylindrical curve if we use this particular Cartesian mesh. So this is the easiest to generate, but the results obtained by this particular Cartesian mesh will not always be that accurate. This is used for very simple type of geometries. Next is structured. In structured, we will first see the monoblock. So within monoblock, what we mean by monoblock is, for preparing the structured mesh, a single type of block is used to cover the entire geometry. This is also used for simple type of shapes where a single block is sufficient for actually covering the entire CAD model. So let's see an example of a cylinder. Now, in order to generate mesh for this cylinder, we can cover this cylinder by a bounding box, which can be a single bounding box, and then generate the mesh for this entire cylinder. So this is called as monoblock, since a single block is used for generating mesh. But what do we mean by structured mesh? Now, structured mesh means the elements are aligned in a specific manner, or they follow a pattern, and hence it seems to be a structured pattern or structured mesh. As you can see, all the elements are following a similar type of pattern along this surface as well as in the volume. So this is called a structured mesh. If the elements are organized in a haphazard manner randomly, is an unstructured mesh. Within structured mesh, the other method that we use to mesh a complex geometry is called as multiblock. Now, let's say within the core of this cylinder, we need to generate a finer mesh or a different type of pattern compared to the outer region. So for that, we have to separate this inner region by using a different block as shown here, and the rest of the bounding region of this cylinder is actually covered by 4 different blocks. Similarly, for this particular catalytic converter type of geometry, since the shape is extremely complex, we cannot cover this shape by a single bounding box. So we generate different bounding box for different shaped regions within the same CFD space, and then combining these blocks, we generate a single structured mesh. So since there are multiple blocks involved in the mesh generation process, this is called as a multi-block structured mesh. Now moving on to the unstructured mesh. Unstructured mesh is the entire discrete cells that we generate within the CFD space are randomly spaced, and they do not follow a single pattern, and hence it is referred to as unstructured mesh. Now within unstructured mesh, we have triangulation or tetrahedron. For 2D we have triangles, and for 3D we have tetrahedron, and as you can see, this entire space is covered by triangles, but they do not form a type of a pattern. They are just filling the particular CFD space by using triangles. Similarly for this as well as this sphere, and this is a volume mesh around a particular valve type of geometry, and that also is filled by packed triangles. But still, this is an unstructured mesh using tetrahedrons or triangles. Coming to unstructured mesh using hexahedron or quadrilaterals, as you can see, this is a distinguishing image which differentiates between a quad mesh which is structured and a quad mesh which is unstructured. So an unstructured hexahedron or quadrilateral mesh is shown to the left hand side. This is all are quadrilateral elements, but they are not following this pattern. As you can see, they are spaced in a random manner in order to cover this shape, whereas on the right hand side, all these quadrilateral elements are following a pattern. They are aligned, or they are positioned in a similar manner. 2D geometry, we have generated a unstructured mesh using quadrilaterals and a structured mesh using quadrilaterals. So this particular mesh on the left hand side is referred to as unstructured mesh using quadrilaterals. For a 3D geometry, we will be using hexahedrons. Coming to hybrid mesh. Hybrid mesh is the most complex mesh, and in order to cover complex type of geometries or shapes, we use different elements, we combine them, and then we capture the shape of the geometry. So as you can see in this particular top corner image, it consists of squares as well as triangles, that is tetrahedrons as well as hexahedrons in the volume. So since the shape is complex, we cannot capture the shape profile by using a single element. So we are using triangles, prisms, wedges as well as hexahedron. Similarly, for the volume mesh inside the sphere, along the sphere surface we are using tetrahedrons, and inside we are using hexahedrons. So combination of shapes gives us the hybrid mesh. The CFD meshing process, as we just discussed, will consist of starting from original geometry, which is a CAD geometry, which can be imported from a CAD software. After that, we extract the CFD domain out of this CAD geometry, which will consist of the domain which is surrounded by wall surfaces or solid surfaces, and which consist of the fluid surface or the fluid volume. So after that, we extract the CFD domain, we generate a surface mesh, and then we generate a volume mesh. So whichever CFD problem you are going to solve, it will consist of first starting from a original geometry, then extracting fluid domain, then creating a surface mesh, or directly creating a volume mesh. So this is done within a single pre-processing software most of the times. Coming to mesh quality, we have seen what is mesh, how to create mesh using a software, what are the different mesh types. But once we have created mesh, how do we judge that that particular mesh will give you accurate results? So there are some terminologies associated with mesh quality as well. Mesh quality as a term is a combination of various mesh parameters which together decide how appropriate that mesh is in order to give accurate CFD results. So better the mesh quality, better the CFD results. Now, in general, as a rule or as observation, compared to tetrahedral mesh, hexahedral mesh will always give you more accurate results because the mesh elements are always aligned with flow direction. But it is not always possible to mesh the entire geometry using hexahedral mesh. So most of the times what we do is within the regions of importance like curving geometry, or where the flow is curved, or where the flow phenomenon is predominant, we use hexahedral mesh or prism mesh in order to capture the flow aligned phenomenon. And away from the boundaries or away from the region of importance where the flow is still or flow is exiting, etc., where we need not capture the exact flow phenomenon that accurately, we use the tetrahedral or other type of elements, and we use mixing of such elements to generate our mesh, which is also having accurate results but which is not having large amount of mesh elements. For judging quality of a mesh, we have three different criterias. First is mesh smoothness, how smooth the mesh is, how it is changing, and whether it is changing abruptly or whether it is changing in a smooth manner. After that, we have the mesh skewness, which is actually a qualitative or a quantitative as well as a quantitative parameter which decides whether the mesh is having large amount of skewness or whether it is an ideal triangle or ideal square. Then we have the mesh aspect ratio, which is the ratio of the largest dimension or the largest length of a mesh element to the smallest length. We will see one by one detail how this is defined mathematically. So first, the mesh skewness. Mesh skewness determines how much the mesh element or cell differ from an ideal mesh element or cell. Now when we talk about 2D, an ideal mesh element will be a square and a triangle, that is an equilateral triangle. And when we talk about 3D, it will be a cube if we are using hexahedron, and for a tetrahedron it will be a tetrahedron, a perfect equilateral tetrahedron. First, when we are saying hexahedral elements, skewness is obtained by definition by the following way. For each of the 6 faces, the angle between the face normal and the vector which is defined by center of the hexahedron and center of the face will be calculated. After that, each value is normalized by the maximum value, so that 0 corresponds to a bad element and 1 corresponds to a perfect cube. So this is mathematical process of calculating the mesh skewness, but in crux or in qualitative manner, in short, it means that how closely your element is to a cube. So if it is a perfect cube, it will have 1. If it is deviating from a perfect cube by a large amount, it will be close to 0. For a triangular element, skewness is defined as the ratio between the area of the element and the area of the ideal equilateral triangle. And for a quadrilateral element, skewness is defined or obtained by connecting the midpoints of each sides with the midpoints of opposite sides and finding the angle between them. So within software, this is used as a mathematical process, but in short, by definition, skewness means how close your element is to the ideal element. Next is mesh aspect ratio, which is the ratio of longest edge length to the shortest edge length. As you can see here, this is a square element which is having a perfect aspect ratio, or the one that we want in an ideal situation, but if we stretch this particular square, the longest edge is becoming very large compared to the shortest edge. So the aspect ratio is increasing, and that means it may not give the best accurate results. Also, for a triangle, an equilateral triangle as shown having sides equal to each other has the perfect aspect ratio, but if we stretch this triangle again, it will give a bad aspect ratio. For a quad, how it is calculated? For a quad element, the vector for each 4 quad nodes form a particular parallelogram. The area of each parallelogram is divided by length of each component vector to give 8 possible aspect ratios. And the minimum of this aspect ratio is taken as the aspect ratio for the quad element. This is how it works inside the software, but basically in short it means it is the ratio of the longest edge to the shortest edge. For a hexahedron, it is defined as the size of the minimum element edge divided by the size of the maximum element edge. Similarly, for a tri or a tetrahedron element, that is for a triangular or a tetrahedron cell element, what Ansys CFD does is it calculates the ratio between the radii of an inscribed sphere to the circumscribed sphere, that is the smaller sphere and the larger sphere, and the ratio of this r inside by r outside of an actual to the r inside and r outside of an ideal element. Ideal element is always a equilateral triangle or a perfect equilateral tetrahedron. For a triangle, this is done by circles, whereas for a tetrahedron, this is done by spheres. And these values are scaled so that 1 refers to a perfect element, whereas 0 refers to a zero volume element, which is stretched to an indefinite extent. Like for an example, if we stretch this particular triangle to a very large extent, it will actually end up having a zero volume. So that is a worst cell or worst aspect ratio cell. Next criteria is mesh smoothness. It determines how the size of the mesh element is changing, because within the entire CFD space we cannot have elements having single size. We have to change the size in order to control our CFD domain mesh count. So we have to use different sizes of mesh in order to fill the space between the CFD volume. So we have to change the size of each cell. We cannot keep the same sized cell within the entire CFD volume. So smooth change means the cell adjacent to a particular cell is having a size approximately same of that, or just increasing by ratio of 1.2 or 20%. So if we see this particular mesh, it consists of large number of triangles, but if you see that adjacent triangles are having approximately same shape, or a shape is increasing by about 20%, whereas in this particular image, this particular triangle is very large compared to this particular triangle. So it is much more than 20%, and which means their mesh size is changing abruptly. It is not a smooth mesh, and a smooth mesh is required in order to capture the changes of the CFD results. So we have to ensure that the mesh is of this type but not of this type. Now there is a term called as mesh density, which determines how closely or coarsely the mesh elements are packed or placed. Because we have to vary the mesh size in different regions of the CFD space, in regions where the flow is very close to the wall, we have to keep a very fine mesh, so that the triangles and quadrilaterals and other shapes are packed together closely in order to capture the boundary layer. But away from the walls, we can, or away from the surfaces, we can have the mesh which is not closely packed together. It can be away, the mesh elements can be larger, and hence it is called as coarsely spaced mesh. So as an example shown here, near this surface of this particular CAD model, we actually are having a very closely packed or finer mesh. But away from this, in this region, we can have a mesh which is having larger size, and hence it is called as coarse mesh. So this change from a closely packed mesh to a coarse mesh is called as changing the mesh density. So how much of mesh elements are packed together in a particular region is called as mesh density. So in regions of flow gradients, the mesh density should be high enough to capture all the flow variables or changes, whereas away from the walls or away from the regions where flow gradients are not present, then in that particular region where not much flow phenomenon is occurring, we can have a low mesh density, so we can have a coarse mesh. So now, as we have seen all the mesh element and as well as the quality parameters, here are some short guidelines which usually commercial CFD engineers or a CFD analyst follows in order to generate mesh. These are not in detail, but this will just give you a view of what exactly is expected. During the training or during any of our courses, very detailed guidelines or very detailed training is given on what to follow and what not to do. So important flow features should be resolved whenever a mesh is generated. So curves, wherever there are any flow changing or flow deviating parts or parts that are very close to wake regions or separations and surfaces along which boundary layer has to be captured. So these has along these surfaces or these regions, a very fine mesh is needed in order to capture the flow phenomenon or resolve the flow phenomenon. Cell aspect ratio should be near 1 wherever there is multi-dimensional flow, or as close as possible to 1. Away from regions of predominant gradients, we can keep the aspect ratio to about 5 to 10. Then changes in the cell elements or cell size should be smooth. That is, our cell shape or cell size should change smoothly. It should not be rapid or abrupt. And ideally the grid spacing should be about 1.2 times. That is, the change in the adjacent cells. Adjacent cells should be larger or smaller, about 1.2 times, not very large than their neighboring cells. And usually if we think about this, what if we say that whenever we have to capture a flow, we are using finer mesh. If we extend that particular philosophy, it means that more the cell count, higher the accuracy. But it is not always possible to mesh or to generate mesh within a large CFD model or large CFD CAD model, because it will actually give a huge mesh count or a huge number of cells, which will be not possible to solve using using a smaller CPU, or it will actually consume a lot memory of the CPU or a large amount of time of the CPU runtime. So the more the mesh count, the longer the project takes. So in order to reduce the CFD simulation project time, we have to use sensible or optimized meshing strategy. So we use non-uniform grids, different types of varying mesh density, as well as different types of mesh elements like hybrid mesh using prism layers, boundary layers, tetrahedrons, hexahedrons, etc. So we do not generate very fine mesh. We always use mixture of mesh in order to generate optimized mesh, not always the large or a huge amount of mesh elements. So we have, in short, during this particular session, we are almost at the end of this presentation. And we have given you an introduction to the entire meshing process, what exactly grid or mesh generation means, how it fits into the CFD process, what is the importance of it, how do we generate mesh using a commercial CFD software, what are the different mesh elements, and how do we use mixture of mesh elements, as well as how do we judge a mesh is appropriate for a CFD simulation or not. So this gave you a overall overview or a summary or just a short exposure to the entire meshing process. So that was the aim of this particular session. But if any one of you or any enthusiast who has interest in CFD, if he wants to learn more than this, or if he wants to become an expert in the meshing or the entire CFD process, in order to enter that particular simulation field, what is needed is basically a strong training which is focused on practical application and practice of the entire meshing process. What is expected from a fresh engineer in order to enter into CFD field and start doing CFD analysis is fundamentals of fluid dynamics and thermal sciences, fundamentals of CFD, how to use a CFD software, how to generate mesh for industrial level problems, how CFD is used in order to make design decisions, and how to make sense of all these CFD results that are obtained. So all this is required in order to get trained, or within the training process, all these elements should be accommodated. If any one of you are interested in going further than just this particular webinar, and if they are interested in getting some type of training in order to use these softwares or in order to do CFD simulations, there are various options, but it is always, but how do we differ from a standard training that is rigid to the classroom type of atmosphere is, we give you flexibility to learn these softwares. So you don't have to travel for learning the CFD process or CFD softwares. You can go through these materials online using our CFD training portal, and you can go through them many number of times. You can also have interactive sessions, WebEx, as well as Skype sessions to clear your doubts, and you have a huge library and huge stock of lectures and tutorials which are prepared by our expert faculties. So all this combined will give you a very flexible training environment if you want to get involved into CFD training and get yourself trained and become a CFD analyst. So we provide this entire in our online training portal through just internet. So all you need is internet, and you can access all our training material online. So what do we offer as a training organization? We offer various courses focused on software uses as well as clearing the fundamentals and making yourself a complete CFD software analyst. So we have a basic course on CFD modeling using Ansys ICEM CFD and Ansys Fluent. We have advanced courses on multi-phase modeling using Ansys Fluent. We have courses on heat transfer modeling as well. These are all focused on industry and how CFD softwares are used in industry, and after completing these courses you can directly enter into CFD simulation field and enter into various industries where simulation is used as design process. So we also have CAD courses which are focused on more on coding rather than analyze the results. So they involve programming a lot. So these are the different courses. There are a lot of many more courses that are available on our training portal, which you can just look up on learncx.com. So in order to reach us, if you want to contact us for any of your training needs or any other queries, you can actually visit our website and just sign up there for free. All these materials will be free, just like this webinar. Just sign up on our website or visit our blog. You can also like us on our Facebook page. There are a lot of free material that is available on our Facebook page as well as Twitter. YouTube, there are free lecture clips that are available on YouTube which you can try. And the best way to reach us is actually just email us at info@learncx.com. Now if you have any questions, we will take those questions in the chat window for about 5 minutes after this session. But before we end this session, we have a demo for you which will be starting in 2 minutes. So just hang on for the demo. This particular demo, which actually it will show you whatever we discuss in this particular webinar. It will show you how to do that entire CFD meshing process for a short type of a CAD model, the entire pre-processing using Ansys CFD, which will start from a import up to meshing.
Hello friends, right now I'm here to give you a demo on how to create a mesh on some random geometry. Okay, right now you might be seeing the GUI of ICM CFD software. The typical process of creating mesh involves importing the CAD model typically from IGS file, but right now we are not going to deal with complex features as it is a time taking process. Right now I'll create the simple geometry, which is a square duct followed by a simple pipe, circular pipe. On that, how to create a structured mesh using multiblock method. So initially I'm trying to create. Don't worry about what are the steps I'm following or not. This is just to give a overall glimpses on how to create a mesh, how the mesh is being created in ICM CFD. I'm just specifying the size of a simple square duct. Yeah. Now a simple square duct of 2 by 2 by 4 size is created. It has created a curves and the surfaces. Okay. So this is the wireframe view, and if I shade it using solid, like it is shaded. Okay. Now we have created a simple square duct. Followed by that, what we are going to do is we are going to create a circular pipe at the back portion. So using some surface creation option, I am choosing the radius of the pipe, circular pipe, and I am fixing the length of the circular pipe using the points. So this seems to be a little bit bigger than what is expected. So I'll just undo the process and reduce the radius. So the next step is creating parts, which is nothing but boundary tags. So for example, this is the way where the flow enters the domain. I'll differentiate it with colors. This is the phase where the flow enters the domain, which we call it as inlet. Suppose the flow exits the domain through this phase, so we call it as outlet, and rest of the portion is wall. But here we'll differentiate using different names. One is pipe wall, and let's say square duct, so duct wall. So now we have different parts generated. One is inlet, through which the flow enters, and outlet, through which the flow exits, and wall. The domain is bounded by, the flow is bounded by the wall, both pipe and the square duct. Now we are done with the geometry. Just before going to the further steps, like which is meshing, I'll just check the connectivity between all the surfaces which are created using build topology option. Okay, I'll just go one step before. Initially, the color of these curves, I'll switch off the surfaces for your understanding. So now we are looking at the colors of the curves. It's like pink in color, and it is a single color. So once we run the build topology, which will tell you the connectivity of the surfaces using different colors. So the red color indicates this line, this particular curve is connected to two different surfaces, which is like top and the side one. Okay, different colors indicate different the connectivity of that particular curve with the surfaces. So right now you don't have to worry about this. Okay, we'll go with blocking. I'm choosing, as this is a simple geometry, I'm choosing to go for multi-block structured hexahedral mesh. I can create tetrahedral mesh much easier than hexahedral, but as this is a simple geometry, we'll see how to create multi-block structured hexahedron in this space. So I'll select the entire space and say create a bounding box, which we used to call as block. Okay, and now this is a monoblock, but if you recollect what you saw in the presentation, there are two different methods in creating block structured mesh. One is monoblock and the multi-block. For this geometry, only single block cannot capture the entire shape of the geometry, so we need to split this bigger bounding box So now more than one block is involved in capturing the shape. So right now I'll switch off the geometry just to show what I have done. So I have splitted this bigger bounding box into two at the location where the shape of the geometry changes from square to circular. Okay, so I have to do anything further to capture the shape of the square duct, because the shape of this left side block is already capturing the square duct. Now I need to do something extra to capture the shape of circular pipe. So now what I have done is I have inserted a block inside the bigger block. Okay, so after inserting, initially there were two blocks. There was a bigger block. I splitted it into two at the location where the shape changes from square to circular. Now to capture the circular pipe, I have inserted one more block inside the bigger blocks. So that inside block, the smaller block, is connected to the outer blocks with four that has splitted the outer box into five. One is the inside one, innermost one, and the other outer on the circumference of it. Now I'm going to delete the unnecessary blocks. Okay, right now the innermost block which we created to capture it captures the circular duct very well. So I'll stop working on the creation of blocks or splitting of the blocks. Now I'll put constraints on the blocks or edges just to guide it to take the shape of the domain or geometry underneath it. If you watch closely, I'll just what I'm doing is I'm just selecting the particular edges and guiding it or applying constraint on those edges not to move other than this particular curve, which is circle. And if you see, I'm applying similar kind of constraints on vertex to the points. What it does is arrests the degree of freedom of that particular vertex to move out of that location. So now I'm done with constraints. The next step is applying number of nodes or number of mesh counts, mesh cell elements on three different directions. One is I, J and K. I is nothing but X, Y, Z directions. So I'll start with Z direction. Let's say particular edge. I selected the particular edge and I gave 31 as number of nodes, and if I show or display the number of cell counts on each and every edge, the edge opposite to that particular edge which I selected also gets the same number of nodes copied. This is the rule or beauty of structured multi-block, because it has to follow the same pattern of mesh elements. So once you have selected a particular edge, for example on this circular pipe, the block created for the circular pipe, I selected one of the edges and changed the number of nodes to 41. All the other parallel edges, not the adjacent edge, but all the parallel or opposite edges gets the same number of nodes. This is a rule of structured multi-block. I'm done with Z direction, which is the flow direction. Now I'll give number of nodes in X and Y directions. So before exporting the mesh, there is something called pre-mesh, which will let you give an idea of how the mesh will look like. I'll just shade it and switch off the edges. So the number of the square block, which was initially like this, after applying the constraint or guiding these edges to take the shape of curve, see, this arrow mark indicates this particular edge is going to take the shape of the curve. So the square block is made to take the shape of the circular duct, circular pipe. So this is how a structured mesh is created. Now further step is checking the quality. There is some quality criteria for structured mesh. So now close to 0 is bad elements and close to 1 is a ideal good element. Okay. So now I just want to see the worst elements in the domain. Okay, I can see all the worst elements are coming in the circular pipe. If I want to improve those, I need to understand why these elements are bad. It seems all the corner elements of particular block, or I would say block created for a circular duct, or having a skewness. This is not a perfect cube or a perfect hexahedron. So I need to do something else, which is O-grid. Just observe here. See, right now the bad elements are present at the corner, right? So now I want to improve it somehow. So what I'm trying to do is not only improving this, and also I need a boundary layer everywhere in the domain wherever there are walls. Don't worry if you are not able to follow this step. This is just an tool which helps you to improve your mesh skewness near the walls and also to create a boundary layer. See, now the corner elements are replaced by perpendicular elements. I'll just replot the quality. Now the quality of the current mesh is more than 0.5, which is more than sufficient for the fluent solver or whichever solver is there. So that's it. Okay, just to I'll go back one step behind and just to show you the difference. Before creating this boundary layer mesh, the skewed elements were there, and near to the wall the spacing first cell near to the wall the spacing is differs, like different spacing is there at different portion of the wall. So after creating the boundary layer mesh and assigning some number of nodes on that, this has improved the skewness and also provide us the boundary layer mesh. So this is the process of creating structured multiblock using ICEM CFD for a simpler geometry.